Okay, so the last week we were looking at the CPT results. So typical record of measured the sleeve and the cone friction is given in this type of diagrams. So basically this will be the output from the continuous recorded CPT test. So what we were looking at is the several methods of integration based on the localized, in fact these the reason why so many methods are there, because it's variations to the empirical coefficients of different cones and basically the integration methods. And you will see here that the calculation is very similar to what we were doing if you are having a strength profiles as layered soils. Here we have a continuous resistance for skin friction and the end bearing, and basically you are trying to do integration from the depth to depth from starting to end, and you have compression and tension capacity. In terms of tension capacity, you do not have the end bearing. So basically it is coming out, and the idea of getting this F jet from the measured cone sleeve friction, this is the sleeve friction, the red color one, is to get the idea of F jet. F jet is the frictional resistance. Now when we look at the various methods, alpha method, beta method, which we were just last classes we were looking at, alpha method is a fraction of is the undrained shear strength, beta method is the fraction of the overburden pressure. We were looking at this F value as representative of each of the type of soil, whether it is clay or sand. Here you have F of jet is to be integrated using this with the recorded the profile of the sleeve friction with several coefficients involved. You can see here A, B, C, D and E, also U and V, which are given in this table for different methods. You can adapt by various locations, like simplified ICP or UWA approach, or Fugro is a private company, but they have been involved in soil investigation for almost 5 decades in various parts of the around the globe. They have established offices, so they have a large experience than anybody else, in fact. So that is why they have proposed this particular method based on what the results they have got. In fact, they have got plenty of data in terms of laboratory test as well as the field test. So they have enough information to propose something like this. So basically also can be used, but you can see here the coefficients vary reasonably from 0.4 to 0.9 for if you look at each category. You can see here is 1, here 0. So that is why these are specific to the areas of interest. Mostly Fugro results are applicable to Middle East, because they have lot of work on Middle Eastern areas, like UWA is predominantly in Australian region. So once you have the F jet value for each of the point that you have got using the value of Q jet. So basic idea is you can use this F jet value and do a integration here to obtain your total capacity. So the whole matter rests on how you get the values of F jet with the measured profiles of sleeve friction and the cone resistance. The idea is these methods are now recognized as an official methods and which can be adopted by any design project, because of API also recommends these methods, as long as in your geotechnical profiles you are having this the measured sleeve friction and the cone resistance. But very seldom people do it, because in deeper water depth as well in deeper bore holes is quite difficult to do it, because the cone penetration requires a lot of effort. Sometimes you may not get a continuous penetration. What will happen is, because the cone can penetrate say 10 meters, you will stop. After that you will excavate that soil, then you will restart the cone penetration. So then you need to actually interlink the top penetration versus the bottom one. So little bit difficulty is there, but established companies like Fugro, they have profile, they have methodology to connect them continuously. So besides the conventional methods of field testing, laboratory testing, and this CPT methods are also recognizable, which can be used. Now the last one, we have seen the capacity calculation involves so many uncertainties, starting from borehole and then to soil sampling and strength assessment, classification of soil and then to establish the friction and this end bearing. So, that is why we have to look at how do we cover these uncertainties, that is one parameter. The second one, all this while we were looking at the failure of the soil by shear and ultimate, that means once the soil is particles are dislocated, they will behave plastically. So, it is the strength what we have evaluated here. If you go back to the equation when we were looking at few days back, these are ultimate capacities, not the I think you are familiar with the working stress methods which we were talking about in the design course. Basically, these are ultimate capacities. We can't allow the foundation to fail when you apply the loads to the structure. So, basic idea is we need to divide this ultimate capacity by certain factor of safety, which will be taking similar to the strength of steel material from yield strength to we are dividing by 1.6, 1.67. So, here we have to divide by certain factor of safety. Now, various codes have different methodology of. If you look at say for example, IS codes on foundations, predominantly on concrete piles and board piles, shallow foundations, they have suggested that factor of safety can vary from 2 to 4, 2 to 5, and leave it to the designer depending on the type of uncertainties involved in the evaluation of soil to the foundation loads to the capacity. You decide whether you want to give a higher factor of safety or, but for board piles they suggest at least a minimum of 2.5 you should provide, and you know, for a shallow footing sometimes you give 3, 3.5 depending on what type of you know, soil investigation. Sometimes you do not have much information, you better design with a higher factor of safety. So, 2.5 is something that you know, most of the pile foundations for coastal structures been designed for, whereas API suggests, because we have you know, the steel tubular piles of deeper penetration, not shallow, not unlike coastal waters, they suggest a minimum factor of safety of 2. Of course, nobody is going to argue if you give a factor of safety of 2.5 or 3, of course, it is going to cost you more effort and money, but as a minimum for offshore structures in loaded piles in compression should have a minimum factor of safety of 2. So, you have a ultimate capacity divided by this factor of safety. So, the factor of safety is to account for uncertainty as well as the loading is working loads, whereas the capacity what we have evaluated at failure. Remember, we started from a bearing capacity of a shallow foundation, we had upper bound, lower bound, all of them were evaluated at failure. We can't allow the foundation to fail, isn't it. So, we need to reduce the loads such that the foundation will be in a safe state when the working loads are applied. So, that is why the factor of safeties are required, and you can see here this table some 6 numbers, in fact 2 columns, tension and compression, both are having similar capacity when it is operating conditions. I think we have defined this in the design courses, the operating versus storm, you know, conventionally occurring you know, frequent interval, which is 1 year return period storm conditions is called operating. Extreme storm condition is the 100-year storm condition. So, basically you have a reduced factor of safety, very similar to what we were discussing about in the design. Is basic idea is higher risk can be taken, that means you allow higher loads to be taken by the foundation, that means reduced factor of safety. Similarly, for seismic condition we have further reduced factor of safety of 1.2 because it is going to be a rare occurrence. So, minimum 2.0, and if you have uncertainty further, you can as a designer can increase the factor of safety, but nobody wants to do it unless you have clear indication from the soil reports that the reports suggest the strength could not be evaluated correctly. In such cases, you may not actually proceed with the project itself, because the risk with the offshore foundation is very high. You go there, you cannot drive, then you have to come back. So, factor of safety is essential to find out what is the working load. So, the relationship between working capacity versus ultimate capacity is called a factor of safety. So, the ratio is ultimate capacity by the allowable capacity, you can call it. Now, how do we find out allowable capacity is just a simple matter of taking the ultimate capacity divided by factor of safety, but then the added information that we need to remember is the weight of the pile and the weight of the soil plug. Remember, we were talking about when you drive the pile inside and just pull out the pile, if the pile is plugged one, what will happen? The soil will come out together with the pile itself. So, vice versa, when you are applying a load to the pile above the seabed, when it is applied say compression load, the pile weight plus the soil weight must be added to the load itself, because it is part of the system. So, that is where we need to make sure use this basically the information. In a plugged case, you will remove the pile weight and the soil weight from the capacity divided by the factor of safety, because it is part of the load, and whereas for unplugged case, that means the soil is supported by soil itself, because this soil is not becoming part of the pile, very similar to solid pile. For example, instead of a tubular pile, if you have a solid concrete pile, what happens? The material of the concrete in the pile itself is becoming part of the load. So, that is what you are. So, that is exactly when it is plugged case, weight of the pile plus weight of the soil must be taken out of the capacity for the buried portion. Of course, the portion above the seabed is anyway part of the load, because you are analyzing the jacket structure. Similarly, for tension, you take advantage of it. When the load is applied upwards, it has to overcome the weight of the pile and the weight of the soil within the pile itself. So, you can add, when you are talking about tensile capacity, is the capacity coming from friction, and add the weight of the plug plus the pile, which is going to give you. So, the more weight you are going to gain, more tension capacity divided by the factor of safety. For unplugged case is only going to be the pile weight. So, this needs to be taken into account, because this can be substantial. Imagine if you are talking about a 100-meter pile, it can give you easily 200 tons of weight. 200 ton is nothing but 2 meganewton. After all, if you look at a pile capacity, maybe 10 meganewton, 15 meganewton. Out of 15 meganewton, if you get 2 meganewton, either for compression or for tension, you are going to detect it here. So, it is almost 10% of the soil capacity itself. So, if you ignore it, for compression you will be over predicting the capacity, for tension you will be under predicting the capacity. So, that is why 10% is not a small amount that you can simply ignore it. So, allowable capacities needs to be taken into account, the weight of the pile and the weight of the soil plug inside. Now, normally we do not know the pile penetration in a design work, which we will have to calculate for several iterations. When you are designing a jacket, you do this analysis and find out what is the pile loads. To determine what penetration is required, you are not going to do everyday calculation separately. So, normally we do something like this pile capacity relationship with the depth of penetration. So, you see this chart, you can see here there are 4 graphs relationships showing the capacity versus the pile penetration below the seabed level, one for compression plugged and unplugged, and the other for tension plugged and unplugged, like what we did just now for the relationship. So, you can see here, once you have the loads calculated from your structural analysis for the superstructure, and you take the loads, come back here, if you need a specifically, for example, 10,000 kilonewton is your compression load, and maybe 8,000 kilonewton is your tensile load, and the piles are plugged. So, you will come here. So, I need 10,000, this is being actual capacity in ultimate. So, you just come here, you read this is the capacity, minimum I require 24 meters of penetration. So, you can decide I need 24 meters. So, that means before you start the design work, you need to generate this graph by simply doing the integration of the resistances coming from friction and the end bearing. So, every level you will add the end bearing at that level, only the friction will be cumulatively added, when the end bearing can be taken at the level at which you are going to consider. So, that is how you plot the. So, you need to learn to generate this. In fact, this will be one of the test or an assignment paper or a tutorial we can do, so that you can understand how this can be generated. It is nothing but you do a layer wise evaluation of the friction, and for that locality you add the friction above plus the end bearing at that point. You move to the next point, you will add the skin friction all above up to seabed plus the end bearing at that particular level. So, you just keep on doing it, and you will get a relationship between the horizontal axis and the vertical axis, which is capacity versus depth. So, you can divide the total soil layers into say every 2 meters or every 1 meter. Each level you will do this evaluation of combined capacity. We will now look at capacity generation for interface layers. For example, I have a only single layer soil of clay or sand, then there is no issues. Whereas, when you are talking about offshore pile systems, for example, you see here multiple layers of alternating types, sand and clay. So, you can see here predominantly clay material, except at several locations at intermediate depths of sand material. Now, you see here this is slightly deeper sand layer, and then you have slightly bigger layer. Now, we want to go to this point, because I want to get certain capacity, that is what you are trying to decide. When you drive this pile all the way from 0 to 100 meters, for example, or 110 meters, you will get an end bearing capacity of that particular layer, because that is going to be very large. So, let me drive that, but while doing so, you are going to puncture through layer 1, layer 2, layer 3, layer 4 of smaller sand layers. As long as you have sufficient effort to drive through, you can drive. If not, what will happen? The pile will stop at that layer, because you have taken a smaller hammer to offshore, you did not evaluate properly. So, what will happen? You are at the starting of this layer, or maybe slightly gone, but you are unable to drive. Either the hammer will break or the pile will fail, because you are trying to overdrive. So, if you stop the pile here, what happened to the capacity? Now, you have a lesser penetration, number 1, and this layer is not too large for you to take the capacity, because it is only a small, say 3 meter or 4 meter. Now, there is eventually there is uncertainty whether that layer is there or slightly lower, whether the thickness is 3 meter, whether the thickness is 2 meter. Now, if that happens, whether can we take the capacity of that layer full, or can we take the capacity reduced, because there is an uncertainty. So, that is where several rules and regulations have been there for last several years. Basically, idea is, when can you take the capacity of an increased layer like sand layer or a rock layer, when can you consider that layer as effective in giving you the resistance? Whenever the layer is sufficient enough depth to avoid punch through. For example, you design in such a way that the pile is resting on this, and if the layer is only 2 meter and or 3 meters whatever, and you apply the load in reality, and if the layer has supposed to be 3 meter happen to be 2 meter, and during the slight overloading of the structures punch through and the pile fail. Now, that to avoid that, we need to have a minimum layer depth, minimum pile must have gone inside the layer itself. So, that is the reason why if it is a smaller layer, we cannot consider full capacity, we need to downgrade the capacity of that. So, that we are in a safer side. So, that is the rules that we want to do. So, that means we need to downgrade the capacity something like this. You can see here in blue color is no correction, the red color is corrections. That means, if you stop the pile at the start of the layer, you cannot consider full capacity, you can only consider a part capacity, and if you go by slightly increasing, you can consider slightly more. So, linear interpolation between the resistance of this layer to this layer, because otherwise there will be a sudden increase. No, you can see the blue color, the same layer gives you a lower capacity, because you are using the capacity of the clay, and the same location if you go to this using this property of the sand, you get a higher capacity. Which one to take? That is where the biggest problem. So, we will normally do a linear interpolation with acceptable penetration depth into the sand layer. So, that is where we are going to see 3 cases. The first case, if you see the this picture, you have a medium sand to a dense sand, transition from sand to sand, but you have a slightly less dense sand on a first layer and a denser sand on the last layer, where I have decided to penetrate into the sand, the denser layer, and then want to take advantage of the capacity. So, you can see from this picture, it has got slightly reduced end bearing capacity, this has got a higher end bearing capacity, but theoretically speaking, when I put the pile on exactly at the interface, I should consider the full capacity of this dense sand layer, but it may not be true for several reasons. One is the variation in the layer thicknesses from what you have learned from the geotechnical investigation to actual situation, plus the distribution of the pressure, the bulb will actually have some effect on the previous layer. So, that is why this minimum 10 diameter, if you have penetration of the pile into the denser layer by 10 diameter, then you can consider that layer capacity as full. So, you can see here, when you penetrated the pile into 10 diameter, you take the capacity of the denser layer, whereas anything less than this you can't take the less denser one, you can do a linear interpolation between the denser layer to the less denser layer. So, that is the idea behind. You see here the Q W is the end bearing capacity of the weaker layer, we call it slightly weaker, whereas Q S is the stronger layer. In between, if you penetrate, for example, you try to penetrate, you think you want to achieve, but you only can drive say 2 diameter, 3 diameter, because the denser layer is having so much of resistance. Then you do a linear interpolation, that means simply Q S minus Q W divided by 10 diameter multiplied by the depth of penetration what you have achieved, and that will be your capacity, which will be including the capacity of the weaker layer. So, something like this has been proposed several years back, but imagine if you have a 2 meter diameter pile, and 10 diameter is 20 meter. If you have to drive 20 meter into a very dense sand, as well becoming impossible. So, API has been collecting lot of information over several decades. Finally, they have come to a conclusion that 3 diameter is good enough to achieve a full capacity. So, hope you understand the idea behind why from 10 diameter we have come down to. So, normally when you try to install a pile foundation, whether it is a concrete pile or a steel pile, if you are able to achieve at least 3 diameter, then you can take the capacity of that layer. If not, you have to use the weaker layer or interface or interpolate between the weaker layer to the stronger layer. So, that is the message that proposed by Lacasse in one of the geotechnical journal, which has been followed, in fact everybody is doing this nowadays, except that API has reduced that idea to 10D to 3 diameter. So, when you are actually going back to this picture now, you can see here what has happened. If you just concentrate on this layer, the starting of the layer, the capacity is calculated based on the previous layer, basically based on the weaker, the clayey material, and then when you have gone down to 3 diameter below, it has achieved full end bearing capacity of sand layer, but in between you see the red color is just linearly interpolating. Comparing the blue one, the blue color is basically with no correction, that means I will have lower capacity and higher capacity like a steps, which is not correct, which is not going to be achievable. So, that is the idea behind the corrections for the interface of layers to layers, which needs to be definitely done. So, that is one from weaker to denser. Like this we have 2-3 cases which will go through quickly. The next one is you have a sand layer and a stiff clay. Of course, arguably clay is not going to offer so much of end bearing capacity, as you can see from the equation, is undrained shear strength is the only parameter which is contributing to your end bearing, which is not going to offer too great, unlike sand layer where the overburden pressure is going to present a good amount of the end bearing resistance. So, in here we have medium clay or it could be sand, either way, and you have a very stiff, and what we are looking at is similar formula. We know very well that 9 Cu is the maximum capacity that you can achieve for clay, and 9 Cu minus 6 Cu divided by 3 diameter. Straight away I have put the API requirement instead of 10 diameter, because we are not practicing 10 diameter. So, we will just use 3 diameter multiplied by. So, it is again a similar linear interpolation from weaker clay layer to a stronger clay layer, only the equation or the resistance is changing from sand to clay. The last one we will be looking at something difficult one. You have a softer or less denser material on top, and we have a slightly different material, but also not very strong, but we have an intermediate layer very similar to the one that you saw here, something like this. We have a sand layer and preceded by clay or less denser sand, and also followed by either a clay or a sand which is less stronger than the layer in question. So, what we need to do is we just need to apply and compile both the things, one is forward and the other one is backward. So, both reduction has to be done, and that is what you see from this picture. If you just go back here, we have done a forward reduction, we have done a backward reduction. You come from bottom to and come and join. So, what will happen if the layer is too small? If the layer is say only 3 meter, 4 meter, so you may not actually achieve full capacity, isn't it? Because we need to come forward reduction by 3 diameter, backward reduction by 3 diameter, and at least you need to have 6 diameter to get the full capacity one place. But if you have only say 3 diameters only, you will see that you will not be able to achieve. That has happened in some places. If you go back to this picture, you can see here the full capacity is this much, whereas the capacity achieved is less, because we are when you are meeting the forward and backward reduction lines, you will come and only just get 50% or 40%. You will get full capacity only when you have the depth of the layer bigger than the twice the requirements of 3D or 10D, whichever is. So, that you need to understand that you are not going to get full capacity unless that is what has happened. So, you have not actually come to the maximum. The maximum is somewhere here. You see, when you are looking at a backward reduction, maximum is some here, whereas the forward reduction comes to meet here, you can't achieve both the capacities, either the capacity of the stronger layer. So, that will be a difficult task when you actually do a computer program or calculation by yourself. And originally we were looking at 10 diameter, but now most of the time we use 3 diameter forward, 3 diameter backward, and wherever the meeting point. And suppose if you have, for example, 10 diameter, what will happen? The graph will be something like this. So, you will see that, isn't it? So, for this will be your 3D and that will be your 3D, remaining 4D will be full capacity, as long as you get that much of depth. So, this stronger layer to weaker layer is predominantly for the purpose of punch through. If this layer is lesser and lesser, we should not consider the end bearing. That is the message that you are trying to get. We call it punch through effect, because many times what happen, you try to locate it there, but slight overloading on the structures will punch through and end up in during operation of the structure, and then you will fail foundation. That is many times happened. So, that is why you have to be a little bit careful there. We will see a quick example. I think the recap of the whole calculation is very simple, mostly geometric, I would say. Surface area multiplied by the length. What you are looking at is the skin friction resistance, end bearing resistance. And skin friction, we have two methods, alpha and beta method, very simple. And then end bearing, empirical formulas are given in relationship with either Cu or with the overburden pressure. And you see here there are 3 layers given to you, 100 meter penetration, and the first layer is predominantly clay, and the second layer is sand, third layer is also clay, but of slightly higher strength. So, you could see the typical pile diameter, wall thickness. Just for practical purposes, I have given one of the recent project. So, basically 100 meter penetration is a typical number you should remember. Most of the offshore pile systems will be something like this, not very small, not too big, 100 to 150 meters, maybe 1 to 3 meter diameter, any diameter that can occur. And the type of loading you can see here, 19 meganewton. So, you should get some kind of practical sense of the magnitude. 19 meganewton is almost 2000 tons. You understand the idea, no? 2000 tons. 28 meganewton is approximately about 3000 tons. So, that is the magnitude of foundation loading. If you just recollect most of the foundation design in onshore structures, something like 100 tons, 200 tons, you will be talking about 300 tons, but not more than that. Handling and such type of numbers you should remember what is the magnitude or order of magnitude when you are designing foundations. So, you can see it is a tenfold increase from onshore to offshore. We normally design foundations onshore maybe not more than 300, 400, 500, even if you look at a multi-story building, several story building, you put so many foundations or so many piles in such a way that the loads are distributed, that is the idea. Whereas, we do exactly opposite in offshore, we cannot put as many piles as we think because of the difficulty we face in offshore installation. So, we actually combine every one of them together with 4 piles or 6 piles which carry multiple times of the same type of pile that carried by onshore foundations. That is the difference that you are looking at. So, you can see here 2000 ton versus 3000 ton is basically for 2 different type of conditions. Why it is given there? Because you are going to evaluate the ultimate capacity. Now, remember 19 meganewton is operating, 28 meganewton is storm. Now, you have a different factor safeties. So, when you multiply 19 multiplied by 2, the ultimate capacity required is 38, whereas 28 multiplied by 1.5 will take you to 28 plus 14 will be 42. So, now you see there are 2 different numbers, one is 42, the other one is 38. Now, you can conclude that it is governed by the storm condition. So, you need to go and look for this 42 meganewton of ultimate capacity as a minimum. So, that is the idea behind why these numbers are given. So, you should look at evaluate what is the factor safety, you should remember and then find out. Similarly, for tension 16 meganewton and 24 meganewton. So, that is where, so required tension capacity is 32 based on 16 meganewton operating and 24 you will add 36. So, you see here 42 meganewton compression is required and 36 meganewton tension is required. Based on this information you go here. So, you could actually get the variety of problems here. You could be asked to find out what is the factor safety, in this case I have asked you to find out the factor safety, or you can actually go vice versa, find out what should be the minimum penetration required to achieve a factor safety as per the code, is not it. So, now you need to do a iterative procedure because it is going to be a problem. The overburden pressure depends on the depth of penetration, but depth of penetration is not known to you. You understand the idea, no? So, that is where the slight twist to the, if it is a forward question like this is very easy because anybody can do it, simply do 2 minutes of calculation. So, you need to learn to practice, unless you practice you will not be able to get things right. So, now let us go to quickly review of this particular problem. All the data are given, you should know how to calculate the areas and geometries and modular ratio. So, you should not ask for formulas. So, you should remember all those information. So, let us look at layer number 1. Layer number 1 is the depth of the layer is 25 meters, density is given, bulk density, which is basically will be provided to you as similar to this sketch will be given to you. And then we have undrained shear strength of 40 kPa. So, 3 information, layer depth and then you have got density, you have got undrained shear strength. Now, we know the procedure for clay. This is basically once you have been given with the undrained shear strength, straight away you should understand it is a clay type of layer, hopefully if you remember, and then use the method which is relevant. So, you should go for alpha method, and alpha method is very simple. You need to find out the undrained shear strength for that layer plus the overburden pressure at the point of interest. Now, you have 25 meter, but if you look at the equation how it varies, alpha is varying with C as well as overburden pressure. Now, if you look at that equation it is to the power minus 0.25, is not it, and strictly speaking you should do divide the total layer into say every 5 meters, every 2 meters depending on the time you have. If it is examination you can divide course, but then normally if you plot the variation of alpha with respect to, if you see that picture I have shown earlier on, it varies non-linearly, it is not a very straight line, but most of the time we accept the approximation of a linear relationship between depth versus alpha. So, for this particular problem what I have done is I have taken at the center of the layer and calculated the alpha value. You could do that for starting of the layer, end of the layer, and in between several points, and then you can plot the capacity depending on the time. For examination point of view, we will do a center of the layer. So, in this particular case, if you look at this formula for overburden pressure is half H 1 multiplied by effective density. Effective density is your bulk density minus water density. All of them I am working on the basis of weight density, not the mass density. So, basically you can see why I have put half, because I am evaluating at the center of that layer. You could do so, you could actually do starting of the layer and ending of the layer and do an average. We know very well that it is non-linear, but still approximation is acceptable. And basic, once you get the P naught and find out the ratio of C by P naught, and you find out what is the value of alpha using the empirical formula given to you, depending on whether the value of the ratio is less than 1 or greater than 1, which we have already explained the other day, and must be limited to 1 if this value comes out higher than 1. That is the that you need to remember. So, once you get 0.67 multiply with C value, you get the skin friction. So, I think this at least this much you should remember. Then calculation of capacity within the layer is pi d times h. Pi d will give you the circumference and h will give you the surface area multiplied by the surface skin friction will give you the skin friction capacity. I think very simple. So, basic idea is this is external, and I have already explained to you we will normally take reduced capacity of 80%, 70% for internal, because the confined soil. So, you calculate the internal surface area by deducting the wall thickness and you get the internal skin friction. So, when you add internal plus external, you have got the capacity of the soil at the inner surface and the outer surface of the steel soil interface. What we have represented is F1 is representing full layer depth. You understand the idea, no? Because we have calculated the center. If you do not want to do so, you can actually do it at the surface, which is at the seabed. You can do it at the end of the layer. You can do an average, or you can do every 1 meter if you have enough time, but the difference is going to be very small. I think I have shown you the plot of alpha with respect to depth. So, that gives you an idea how you calculate for one single layer. When you go to the second layer, we will just quickly look at second layer. The only difference is this is being sand, method becomes beta method instead of alpha method, but the overburden pressure you can see here, overburden pressure for the second layer I have taken half the depth, but cumulatively add with the weight of that first layer. That is very important. If forgotten, then all the results will be wrong. Remaining is all just putting together numbers. In this particular problem, we have used direct calculation of beta based on phi value, because that is given to you here. If you go to the problem, its phi value is given, you have not been given with beta directly. If you use a new API code, you will be given directly beta, but in this particular case phi 2 is given. So, you calculate the delta value and then correspondingly you calculate the beta value is k, p naught and tan delta, which I think you should remember. So, all these formulas will not be given. The formula that is supposed to be given, I have already given information, only the table will be given if required. Then you calculate this internal external capacity by simple means of pi dh internal, pi dh external, and then we go to the last layer, exactly do the same thing, only thing is add the layer 1 and 2 full weight, layer 3 you take the middle of the layer for skin friction, and this is being a clay layer, you do repeat the procedure. In this particular case what has happened, now alpha becomes 1, because the overburden is so much that we should not take the values of higher than 1. So, limit it. Then come to the end bearing. End bearing what you need to do is, if you go back here, when you are evaluating the end bearing at this point, you cannot use the previously calculated P naught value at the middle of the third layer. We have to recalculate the P naught at the end of the pile. This sometimes people make mistake, because take that half value and then you cannot do it, because For skin friction, representative is the middle of the third layer. For end bearing, you have to recalculate the P naught value or the overburden pressure at the tip of the pile. You need to recalculate. I think it is done somewhere here, or it is not done. Yes, it is not done here. I think annular end bearing Q values. This is done, is clear, but this is only for skin friction. But for end bearing, I think it's not required for clay type of soil, but if it is a sandy type of material, then NQ times P naught will come. In this particular case, you have NC is a empirical value given as 9, so you do not need to worry. But when it is a sand layer, you have to recalculate this P naught by replacing this 0.5 with 1, and then use that P naught for. But in this particular case, it has become no problem, because we have C times NC, NC is 9. So, once you do this, then you have got the two types of end bearing, annular end bearing and total end bearing. Then the corresponding calculations, whatever I was trying to explain, determine whether the pile is plugged or not plugged, summation of internal friction, all those things can be followed. And then ultimately, ultimate capacity in tension, ultimate capacity in compression, and then use the formulas to divide by the factor of safety to compare whether you have sufficient capacity or not.